classification of orders. Sorry. Okay. So it's worth mentioning this for a moment. There's two, in data science or data mining, there's two main types of problems that you encounter. There's supervised, and then there's unsupervised. Okay. Now, can somebody tell me the difference between these two? Very, very simple. What is it?
One basically saying, yes, this is a good answer, no, this isn't a good answer, and the other one just kind of
yeah, so that is correct. But let's even break it down in terms of what is missing in an unsupervised model.
Unsupervised, you have like a y variable and a response variable.
In supervised, you have
Yeah.
Does that make sense?
Unsupervised, you don't.
That's it. That's the main thing. So here we have y is the response, and the y is supervising the training test. That's where we say that. And here we do not have a y. Right? But you have features in both cases. So x1 all the way through x, whatever p. These are the features. And then you still have the features, x1 all the way through x, p. Okay? All right. So now there's a handful of techniques that you're going to encounter in your training related to these. But what's kind of the canonical supervised model? It's like the most basic supervised model you can think of.
Linear regression.
Linear regression. Thank you. Does that make sense to everybody? So here we have regression. All right, specifically linear. And then what's the canonical model for unsupervised? There might be two answers to this. What, maybe not just a specific model, but what, you don't really have a y governing the answers here. So you just have a bunch of x's floating around.
Like
How about
classification.
well, classification technically falls into the supervised setting, but clustering, that's unsupervised. Another thing is PCA, principal component analysis. You can combine some of these things. You can do like PCA and then do supervised tests on it. But this is kind of the setup. Now, to further this notion, we have linear regression, right? But we can actually split supervised into two categories. So let me erase this and split this into two now. So what type of supervised tasks do we want to actually perform? What's one of them? Actually, that's totally the right idea, but I'm going to use a different word. It's a quantitative response, which is actually regression. And what's the other? Classification. Does that make sense? So, and then from here, I mean, there's just so many models, right? That's the problem. So you have parametric models, non-parametric models, right? Parametric means parameter, so like the regression coefficients. Non-parametric means no parameters, like excluding parameters, those are not parameters. So regression, you have linear regression, right? Classification, you have, what's the first natural classification model? K and N, K nearest neighbors, right? Turns out you can do a K and N for regression also, right? I think there would be a more natural way to write this down. How about logistic? That's classification. It's called logistic regression, even though it's in the regression section. Don't worry about that, K and N. Then you have a whole list of potential models throughout data sets, right? That's really all, that's what it is. It's not, we have all these special names for a field that really is just.
So it was K and N.
K and N is K nearest neighbors. And let me continue on this for one moment. Okay. So, and this is actually the first thing in the notes, so it's not going to be horrible timing. But in a regression setting versus a classification setting, your model, it's always going to be the same model fundamentally. It's always going to be y equals f of x plus epsilon, right? But if you're in regression, y's are quantitative variables, right? If you're in classification, y's are labels. They're like, do you have the disease or not, right? Gender, whatever it is, okay? So another way to look at this model is that this is a conditional expectation, okay? So in regression, you think of f of x as being like the expected value of y given x, okay? But how do we relate that in classification? Well, we think of it, it's called a Bayes classifier. We think of the probability of the event y given x. So it's not exactly the same, but it's analogous. Okay, so we're trying to estimate, this is a little loose on purpose. When I underline x, it means there's multiple features. But how do you classify something? You say, given a value of x, is it more likely to be in group A or B? It's just the highest probability, that's it. Does that make sense? So this one actually predicts the values of a curve. This is saying which one's going to be a higher probability. And that's basically every single method. It's always the same game over and over and over. So what we're going to start with today is classification, and that's what we left off with last class. And there's a pretty significant R coding portion in this set of slides. And then the lab's going to extend off that. Okay. So what we're focusing on right now, supervised learning, meaning we have a response to deal with, right? Which is good, it's easier. And we're going to start with classification. We already did regression, linear regression. The problem with this class is we're just mixing and matching topics, right? It's intended to be kind of a prerequisite for a machine learning course. So you'll learn more of these things. So we did linear regression. Now we're going to do K&N classification, okay? Arguably, logistic regression is the most famous classification, widely used, but you'll see it most definitely before you graduate, okay? Or whatever part of your academic career, you're going to see this, okay? All right. So we studied linear regression for use when we want to predict a quantitative response variable. That's the whole notion, right? Quantitative response, linear regression. If we want to have a categorical response, or what if we have a categorical response variable? So think of examples, like what are classic classification questions? Anything. Just does everybody understand what that means? I know I'm not trying to be too basic here, but it's labels like, disease or not. Did they die or survive on the Titanic? That's a famous classification data set, the one that you did for the first one. Okay. Anyway. So then the study of predicting categorical response variables is called classification, technically in a supervised sense. So here's some examples. A person has symptoms that could possibly be attributed to one of 3 medical conditions. So based on data, which one of the conditions is most likely? Okay. A bank must be able to determine whether an online transaction is fraudulent on the basis of a user's IP address, past transaction history, etc. Right? Using DNA sequence data for patients with and without a disease, a biologist would like to figure out which DNA mutations cause diseases and which do not. Right, so think like, how expensive are some of these DNA studies before you actually conduct these? Why, if you throw a machine learning model on it, it's so cheap. It's literally just a laptop. Right? It's like you can get an idea of what's going on before you have to conduct this expensive medical study. Okay? So here are a few classification methods. Technically, these all fall under this bullet right here. Okay. we have logistic regression, most famous classification technique. Linear discriminant analysis, really, really cool technique. Requires a little bit of machinery. What you do is you assume normal curves. You have to have continuous features for linear discriminant analysis. You can't have categorical features, but you just assume they're normal and you just see which one has the highest probability. That's it, essentially. K-nearest neighbors is what we're going to do today. Most intuitive classification approach. Trees and random forests. You can actually do trees and random forests for regression as well. This classification. Support vector machines. Really cool. Requires much more machinery. That finds a maximum margin hyperplane between 2 points, whatever that is. So, again, you'll see these things in other courses. So here's the setup. Just as in regression, we have a set of training observations. Right? So remember last class, I briefly discussed the notion of training and test data. Is everyone clear on that? Great. You have, whether you partition the data into 2 data sets or whatever technique you're using, that's the most intuitive notion. Let's assume that we build the model off the training data set, okay? So we use the data to build the classifier. In other words, create some model. We want our classifier to perform well, not only on the training data, but also on test observations. Otherwise, this whole field is useless, right? You need to be able to build a model so it actually does well outside of your data set, okay? So, all right. Sometimes I'm loose too. This isn't just a single feature. There could be multiple features here, right? There could be like, age, height, blah, 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 classifying just disease. Technically, the first one should be bold, right? But, okay. So, assessing the model accuracy, recall for linear regression, we calculated the training mean square error. So what does this represent? It's the distance of the predicted function against the actual cases, right? So you're just curious how well you do at predictions, right? So we're taking these vertical distances. This is the training data, though. Not the test data, and we look at the vertical square distances. That's a measure of error, right? These are this is how off our model is from the actual cases, and we average that. That's training error, okay? Test error would be the same line. So this is training. So what would a picture of test look like? So it's the same model on a different data set, right? Maybe we didn't do a very good job. Does that make sense? So this is the test. So notice it's not the line of best fit anymore because we trained the model to be the best with the training data. And then we're trying to use this model on a new data set, which might not do very well. Maybe it does better than this, who knows, okay? So how do we quantify, it's such an intuitive notion, how do we quantify an error rate for classification? You just look at the number of misclassified cases from your model. Okay, does that make sense? Is there other questions about that? What is this I? It's a what function? Indicator. It's an indicator function, right? All this is saying is we're going to sum across all the values that were misclassified, and if you average this. So you're adding a bunch of zeros and ones up and you're dividing by n. This is a proportion. Does that make sense? It's the proportion of misclassified cases coming from the model. Are there questions about that? Please.
What does the indicator function mean?
So by definition,
Like, could you just write yi does not equal y hat I?
well, it's just realize, okay, like if you were to create a column for the indicator function in a data set related to y I not equal to yi hat, and then here you have y, and here you have yi hat, right? So this is like has the disease, does not have the disease, has the disease, has the disease. That's the real data, right? So here we correctly classified this one, but then we didn't correctly classify that one, right? So this is a sequence of zeros and ones. Does that make sense? What's this one gonna be? So
Or
it's
zero.
right. Does that make sense? Because it's this if it was equals, then this would be a 1, right? So it's 0, 0, 1, 0. These should line up there. Point being, what's the error? What's the final formula in this simple example? We have a 75% correct classification rate, right? So a 25%. So 0.25 is this 1/4 sum of the indicator values. Does that make sense? It's just adding this dividing by 4. So,
But so does the indicator mean anything? Like, why couldn't you just have that column when yi does not equal y hat I?
because the indicator in a mathematical definition it's an on or an off. It's a 1 or a 0. So it's just a way to quantify it, like analytically, I guess you'd say. So if you're curious too, the indicator is for any set, the indicator function as a function of x over a set that's going to be 1 if x is in A and it's 0 if x is not in A. Does that make sense? That's the mathematical definition of an indicator function.
So it is true that the error rate is simply just the proportion of misclarified observations.
That is exactly what you should be getting at.
So what is the top sentence? We copy it to training mean square error. What is that?
So we have in every machine learning model, you have 2 different types of error. You have training error and you have test error. Does that make sense? So I mean, it's really intuitive. They're defined exactly the same. They're just over different data sets. It's just you have to be mindful that the test error comes from the trained model. Does that make sense? So,
Training mean square.
yeah. So you're going to define it very similarly. You just have to use the y hat for the trained model. Okay. Are there any questions about this before we building the foundation? Okay. So similarly to regression, the following is referred as the training error, right? It's the thing on the previous slide. So the test error associated with this is exactly the same formula. The reason I'm using average is because I don't know how many cases are in the test data set now. I mean, you could just define it beforehand, right? Maybe it's 1/10 of the original data set. I don't know. But I could have written it as like 1/n star, blah, blah, blah. Does that make sense? Just a different sample size. We're just going to use average instead. But be mindful. Okay, this is the test data, and this is the test response from our trained model. Okay, does that make sense? It's kind of tricky to get that through your head to be able to see this. So obviously, a good classifier is one for which the test error is the smallest, because that means you're minimizing the error on new data sets. Okay. So the best classifier in terms of test error assigns each observation to the most likely class given its predictor values. So what am I saying there? You compute the probability of being in a certain class, and you want the one that has the highest probability. It's exactly what I had on the board earlier. This is actually called a Bayes classifier. So assign test observations with predictor variable x test to class J for which P of y equals J given x equals x test is largest. So if you understand the first bullet right here, you understand the basis of every commonly used classifier. Okay? Some of them are a little bit, like support vector machines are a little different, you know, but linear discriminant analysis uses this, KNN uses this. You can use logistic for this if you wanted to. It's not always used like that. But all these common classifying techniques come from this Bayes type formulation. Okay, you just stick it in the model, see which one has the highest probability. That tells you over. Okay, and you could call this a conditional probability, or we'll just use Bayes rule. Remember, Bayes rule is a type of conditional probability for your intro to stats course. So that's why it's called a Bayes classification. Questions? All right. So I'll consider a two-class problem. We're going to make our life easy for the moment, meaning y-test is either class A or class B. So the Bayes classifier, it predicts A if the probability of y equals A given x equals x test is greater than 0.5. That makes sense, right? Yes.
In practice, would Trevor just want to report like the probabilities of it's 50% chance and about say 50%? Or would you
Yeah,
always just
that would be meaningful in certain situations. Like,
what is
especially
it
for
called? Still Bayes classifier? Bayes
Well-
always reports just the classification. And not
Okay, so it just depends on your goal. Like, if you're just trying to like, for example, when you're spam filtering, it's going to choose spam or ham.
right.
It's not going to give you the probability of it going into one of them, right? So that's not going to care about that. It's going to automatically choose it for you, right? But maybe if in more delicate situations, if you're on a borderline situation, you might want to know the actual probability. So logistic regression, for example, it's a model that gives you the likelihood of being in one of the categories. But then you can use that as a classification by saying if it's bigger than 0.5, it's in this one at a very surface level. But the point being, like, yeah, like you get meaningful results by looking at the probability of being in that group as well. That's just another way. Okay, so these pictures were taken out of the textbook, the Introduction to Statistical Learning, and here we have simulated data of 100 observations, response Y, either blue or orange. So this is, we knew the truth here, we simulated the data, okay? With predictors X1 and X2, these are quantitative predictors, and obviously a dichotomous response, right? Hence the binary classifier. And so this is the true Bayes decision boundary. Notice that because of random error, you can still have cases that fall on either side. Does that make sense? So just think statistically for a moment, right? It's not like every point falls on the line. When you generate a model from in a regression sense, they're not all falling on the line. There's random error. So that's illustrating in a classification sense.
So what is purple line represents? It is real or just calculated model over
The dashed line.
the dashed line.
So what that represents is the true Bayes classifying line where the probability is decided to be majority, like 0.5. But realize that if we're simulating data based on a true line, then you're still going to have noise. So once in a while, you're going to have orange cases over here. Does that make sense? Just think regression, right? If you simulate the model, y equals 3 minus 4x plus epsilon. Here's the line, 3 minus 4x, but what's your data going to look like? It's not going to all be on the line. It's going to look like a scatter plot. Does that make sense? This is the true model, though. This is the truth, right? But your data is dispersed about the line. So in a classification sense, this is the truth, and then you have data all scattered around this, but ideally, you want to predict the actual Bayes decision boundary, right? That you want to predict. That's like the truth. You want to predict this. Does that make sense?
That means the randomness is from the epsilon.
Yeah, but it's almost like that. So there's no like normality assumption imposed, but it's totally analogous to that. So if you can think of it like the epsilon, then that's good. But it's not exactly a normal distribution there. So, is everyone clear on that? Okay. All right. Okay, so in theory, we would like to always use the Bayes classifier. In practice, we don't actually know the truth, obviously. That's like, we don't know the true linear model, so you predict it. Does that make sense? Just a normal statistical concept. So K nearest neighbors is the classification technique we're going to look at today. And it estimates probability of y given x, and then classifies observations to the class with the highest estimated probability. And it's the most, hands down, the most intuitive classification technique ever. It's really, really nice. Maybe the formulas are confusing you, but when you see it in a picture, it's like crystal clear, okay? So, given a positive integer k and a test observation x test, identify k points in the training data closest to x test. Label script n, like a neighborhood, that's why we use n. So n sub test. Estimate conditional probability for class J as a fraction of points in n test whose response values equal j. So this is all we have to do. This is the formula. Technically there should be a hat here, but that's fine. Just because it's not the truth, right? We were trying to predict the truth. But P of y equals j class. Given test data, it's the so let's say your neighborhood's like 5. You look at all the closest 5 points and you just see out of the 5 which ones fall into which category. Does that make sense? So again, we're summing up zeros and ones. It's just the proportion of values that are whatever class. Okay. So before I move on, what's that formula?
It is still the proportion of misclassified terms, but just within the neighborhood.
This time it's the proportion of, okay, so let's say you have 2 levels for your response. Then you have, how many probabilities do you compute? 2, and you just pick the highest one. Does that make sense? That's all. Okay. So you'll have to do it for j equals, orange and blue or whatever the, I don't know, whatever the diseases are, whatever levels of your categorical variable. Okay, so here's a basic picture. Very, very simple classification setting. Let's say we have these handful of points, training data with 6 blue and 6 orange observations. And we're going to use a neighborhood of 3, okay? And the decision boundary based on a 3 in n, right, k in n. Notice for this one single test point, you just radially go out until you've captured 3 cases. So which one wins? Blue or orange? Blue. Does that make sense to everybody? You could technically compute the 2 probabilities. They would be 1/3 and 2/3, right? Since it's dichotomous, you only need to compute 1. Yes?
So does k always need to be odd then?
That's a good question. So in situations, you should choose to be odd, yes. You want to be safe. But it just depends on like the way the data is looked at. But yeah, you could just arbitrarily choose one of the 2 cases if you have a tie. I mean, there's a lot of ways to fix it. So. All right, so this is fascinating. Like, we generated the truth as the dashed line, and look at how well the k equals 10 performed. Does that make sense? It's pretty amazing, actually. So, we knew truth here, and then we used our model to predict the actual decision boundary, just the most basic classification model, and we actually did pretty well. Okay. And then how do we do this? We just pretty much scan through all these grid points, the smaller grid points, and just see which case it falls in. Does that make sense? So there's a bunch of test points here, okay? And then from that we can see how to construct a decision. So there's a little bit going on behind the scenes. The previous picture. Sure. So this is the basis picture. So right here, the test points are the x's. It's the center of the radius. And then you expand that radius until, notice it's k equals 3 specifically. If I would have done k equals 5, it would just be a bigger radius. Let's pick odd numbers for the moment. So notice that, how do we decide, if we were to have a point where the x is, would that be orange or blue? It would be blue because there's more blues in that neighborhood, that's it. But realize k now is subjective, like it's a tuning parameter. We have to choose k. Why? What would happen if you chose k equals 1? You would overfit the model, right? You would always, if you picked any point near the blue one, it would be blue, right? Etc. So, but if you picked k to be the entire data set, then it would just be whichever has the most of that color. Do you see what I mean? So that's underfitting the model. So
I think in this case, if k is 3, so we just predict that the cross, the x is blue.
So think where the cross is, that's like a new point. That's the whole point. That's the test cases for the x's. It's the center of our circle, okay? Yes.
Can you go to that other slide you showed?
Sure. Before.
Yeah, that one.
Okay.
So is the dotted line where there's like 5 of each?
So the dotted line is as if we simulated a data set with the true phase classifier.
Well, so K is 10, and the dotted line, if that's the decision boundary, then is that where, like, when K is 10, you have 5 orange and 5 blue, so therefore that's like the decision boundary?
Well, it's so there's no notion of n, or my bad, of k until we try to predict the dotted line. So when we simulated the data, there was no k.
Yeah, I mean when you're predicting the dotted
When we're predicting the dotted line, we could have done it with different tuning parameters, and this one happened to fit the best. But maybe I'm not understanding the question.
like on that dotted line, if you chose a point
Yes.
and you went out to like the K10 nearest neighbors,
Yes.
then would you have 5 orange and 5 blue, and that's why that's the
Yes.
dotted line.
Yes. My bad. I understand the question. Yes. Does that make sense?
And so then you found those points, and then you just drew a line across all those points where it's 5 and 5.
Essentially, that's what it is. But you know, another way to look at it is for every one of these small dots, you did a 10 and n and just labeled it blue or orange, and then it crossed over here. Does that make sense? So that's the way they probably simulated it on the computers, to run through the actual pair of small dots.
I see.
But what you said is not kind of what Okay, so just to get an idea, it's another important notion in machine learning and data science is overfitting and underfitting. Okay, so if you make k, remember we have to figure out what k is. We haven't really talked about too many techniques to choose. We're going to do that in the lab today. But if k is 1, then you are overfitting. So you're doing a poor job at predicting the true decision boundary. But if k is too big, then you're underfitting, okay? And it's analogous to, in a regression sense, if you just keep throwing predictions in the model, then you can also overfit a model. So are there questions about this picture? Or both pictures? Yes, please.
I guess in a sense, the only reason why you would know if it's overfit or underfit is because it doesn't match along with the other line, or?
Well, here's the problem. In practice, you don't know the other one.
Yeah.
Does that make sense? So there's kind of an art to knowing what overfitting and underfitting is, but we have techniques of choosing k. Like cross-validation is the one thing. So, and hopefully that does a good job at balancing that. Yeah.
Why are there something that K equals 100, right? Because if there's 100 data points, aren't you just going to say everything is one or the other?
Well,
Everything's one.
Okay, so there's actually more than 100 points, but I would agree. Yes, if you actually extend it to the entire sample size, then,
Then you're just saying everything is. Okay.
but here there's more than 100.
And so then when K equals 1, you're saying how do you come up with a boundary for that?
Well, again, you scan through all the test data and you go out radially until you hit 1 point.
Okay.
And then here's where it's going to cross over. You notice that this is part of the decision boundary. So that little neighborhood around the yeah, because that's so that's why it's not a very meaningful interpretation, right? It's like, sometimes that might be meaningful if you had a bunch of people over here, but does that make sense?
Yeah.
All right. So as in the regression, training error, not a good predictor of test error. You can arbitrarily get your training error as small as you want, especially in a KNN, right? You can almost get it to be 0. You can pretty much get it to be 0, right? Perfect predictions in the training data set. That's useless in a testing sense. So can we predict the direction? This is a great example. I love taking data sets from Introduction to Statistical Learning text. So can we predict the direction of the stock market today using the previous 2 days' movements? That seems like a very, very powerful question to ask, right? So it's pretty fun. So this is in the Introduction to Statistical Learning package, and it's the SmartIt dataset. Okay. So let's look at this. Here's how it works. We have a bunch of different years. My bad. A bunch of different days for years, right? Because we have I forget how far it goes, but anyway, we have whatever 365 days or however many training days there are for 2001, etc. Then we have lags, and then we have volume, and then we have the actual today's values. Not today, but whenever the data set was collected. So if this is in days, what does lag 1 represent?
Previous day.
The previous day, right? And this is a common time series notion. If you took a course on time series, you're probably going, why are we using a k-inf time series? It's okay, right? It's not like the most sophisticated approach to do to look at serial correlation, but it's actually pretty cool because we are using dependence structure in this, you know? So anyway, you can kind of see the pattern, right? Notice that lag 1 is 0.381, lag 2, that same number corresponds. Does that make sense? So lag 5 is like 5 days. So this is a whole week where the trading is. A little bit about the data set. The year that the observation was reported, lag X, percentage of X days ago. Volume of shares traded, number of daily shares traded in billions. Today, percentage returns for today. Direction. So this is our dichotomous response, right? So we want to see if there is a positive or negative return on that given day. So if there's some kind of serial correlation, maybe if we could use the day before, exploit the pattern, then we can make money, right? Does that make sense? So factor with levels down and up indicating whether the market had a positive or negative return on a given day. Let me try to motivate why we're doing this. So what am I doing here? Can somebody explain this code? Maybe look at it for 30 seconds to see if you can explain what the motivation of this is. Pretty much. So notice if you look at lag 1, right? Then if you extract the direction, this is a negative number. So in other words, if it was negative average returns on the previous day, then that might support that it's positive on the next day. Does that make sense? Opposite. Okay. That's like an AR1, right? Autoregressive 1 model. If you take a time series, maybe that's very simple. AR1, but not saying that's the correct model here. Okay. So then you're going to look at the picture and say, how on earth are we going to classify that? Right? So it's chaos. So you can already anticipate we're not going to do a very good job. Little review on how to create a plot. Everybody was pretty comfortable with this on the exam, for the most part. Anyway, splitting it up into down or up, and only for 2 lags. Does that make sense? There's 5 lags in the data set. We're only going to use 2 days before, okay? Since it's kind of appropriate for today's lecture, given the setup. So let's pick a point, or my bad, first let's look at the procedure. How do we actually construct a KNN? Well, we calculate the Euclidean distance. Why not use Euclidean distance? It's a very natural metric to use between a new point and all data points. So for a single data point, so that's it. Notice this is a single data point. Does that make sense? So that's like the x value, okay? Or my bad, that's not the x. Right now, it doesn't really matter fundamentally. The new point, new, is the test case, and these are the actual lags. Does that make sense? So if you have a new lag, these are the test points. You compute all the squared Euclidean distances. So we have the whole set of distances, okay? And then create a set in new containing the k closest points. So you have all the distances, and then you can just use a simple R function to find the closest points, right? Determine the number of ups and downs in the neighborhood and classify the new point. That's it. So before I move on, does this make sense mathematically?
Maybe go over it once more.
Sure. So it's the same notion as the previous slides, but essentially you pick a point. Let's say this is this market data. Right? And then what's my test point going to look like? I have to use a different symbol. Let's say it looks like that, right? Now we have, so 1, 2, 3, 4, 5, 6, 7, 8 points. So how many distances are there going to be from this point? Just 8, not a trick question, right? Yeah. So we compute all the Euclidean distances from that single point. Okay. And then we have 8 distances. And then we just pick the, so we could do a 1 NN all the way through an 8 NN on this basic example I just made up. If you do a 1 NN, it's going to be classified by that point. 2, it's going to be these 2, etc. Does that make sense? But why not just compute every single one at once? We'll just find all, however many distances there are. That's how we're going to construct this.
So what is the difference of this from the one we talked about before, being looking for the fractions?
It's exactly the same. It's just an applied example of the game.
It's just easy since we are going to calculate the distance. Yeah.
Yes. I'm just saying, like, okay, so before we had a radius and we didn't say how we compute distance. We just said it's the closest. Now we're actually defining it in terms of Euclidean distance. Okay. So this is the start of our function. We won't actually stick this in a function, so we're going to build our own k and n function. And let's start by testing some point. So notice, these are our test points. Does everybody understand that? Those are tests. Okay. So we're considering the points 2, 4.25. We'll choose k equals 5. We can change that though. Okay, that's the neighborhood. And notice, remember how our operations work? You take all of lag 1, subtract the test point. So I don't know how many cases there are in this. Let's just say there's 100 for the moment. How many distances are there going to be then? 100, right? And then we use the order function. And this could be a little counterintuitive if you haven't used the order function. It gives you a permutation of all the closest distances, essentially, so that we can extract those. So if you just look at the first k values being outputted of the order function, that corresponds to the closest values and radially to the test point.
It's just giving you the distances.
So the distances come from the actual, you can see the square root computation.
Yeah.
Order is a different function that just orders it, essentially, gives you a permutation of what the order, or how, in terms of magnitude. Like,
Oh, so you get the actual like x and y values, not just the distance.
no, you get just the distance, but that's all we need. So then we can extract the correct cases, actually.
But don't you still need to know which group each of those is classified in? The nearest k.
Yeah. So basically, the order function is going to tell you what rows to extract
Oh,
that correspond to the closest cases.
so it's giving you the row numbers.
Yes, but then we can take the row numbers and only extract direction out of that, because that's really what we're talking about is the response.
Right.
But that's good. Those are good questions, because that's the confusion with the order function. Right? Is everyone clear on that? Now, if you're a little confused on the order function, play around with it. It's just make a vector up of values and just apply order on that and see what it does. But you can just take on faith also that it just extracts the correct rows corresponding to the closest distances of the flags, okay? And then, this is one way to do it. I mean, there's multiple ways to do this. Why not use the table function and take which max, of course, so like, there's only two, right? It's not like you really need to use the table function, but what if we had, 10 levels of some variable, then that would be a very slick way to do it, right? But the table function is going to return how many cases fall in either up or down, and then we'll just pick whichever one's the max. So the choice for this specific test point is down. Does that make sense?
Just want to confirm on the order function. So does it just, does the order function just take the first k points whose distance is the smallest in this case?
Yes. Yes. There's other ways to. You can use the sort function as well to accomplish the same task, but I think I just like this.
So this function just order down automatically and extract the first k elements.
Yes. So it seems like computationally inefficient to always compute all distances, but it works. Does that make sense? So there's more sophisticated ways to approach this problem, not just practice, since it's kind of redundant to find everything. But. So this is a picture of that specific test point from the previous slide, and you can see that there are 3 downs and 2 ups corresponding to that test point. Hence, we pick down. Okay. So that's the algorithm, or the little bit of code on the previous slide is describing that picture. Okay. Yeah, so if you radially extend the test point is where the cross is now. Right. If you radially extend, you can see 1, 2, 3 black points and 2 red. And so that means that our choice of that, if we were to have a value that existed at that x, it would most likely be down, because there's more downs than ups in that radius. Specifically using k equals 5. Does that make sense? Okay. I'll tell you what, let's skip this task. But in principle, it would be nice if you could do this. Write a function called knn decision that returns the class decision for any new point and any choice. So in other words, just take the code that I had a couple slides ago and just make it a function. Does that make sense? But I have the function prepared for you guys just to save time. There it is. Okay. So I guess you should be able to do that in principle, right? You just write a function. So notice, we generalize this a little bit. Now we're defaulting. We have 2 test points. K is defaulted at 5, right? So we don't actually have to enter the value k each time. It'll just default to 5 or whatever you want. Notice that it defaults lag1 and lag2 specifically out of the SmartGit data set. So you could pick any data set and this function will work. It's pretty nice. And then direction is the SmartGit direction as default. Does that make sense? So it's still hard coding a little bit, right? We're kind of referencing that specific data frame. Length in, we have some stop if nots because we are computing a vector of distances, so we want the length of lag2 to be equal to the sample size, and we want the length of the test points to be equal to 1 because our function is not very generalized. It only sticks in a single test point. Okay, does that make sense? Then everything else is the same. This is all the same code from the previous couple of slides. I take the square root, Euclidean distance, and then I use the order function. You could also use the sort function if you wanted to, and then you just extract those points. Okay, and it returns them. Yes.
So just want to make sure K stands for the number of points close to the chosen point.
Yes. Yes.
So that means that for all the points, the radius will be
Yes. So it just turns out, yeah, it'll work out though. Yeah. So you have to. So technically, it's computationally there's a lot going on because, like if you want to find the prediction error or the test error, you'd have to go through all those cases. Does that make sense? But yes, you would have to do it because this will change for different values of test cases. So all this is doing is putting in one test point and outputting a single classified value. That's all the functions do. Okay, so let's build our model using data from 2001 to 2004 and use the 2005 data as a test. So that seems reasonable, right? So in other words, we're trying to introduce the notion of, test error versus training error. So let's actually train the model off this data set and see how well the trained model works with 2005 being the test data. So we can predict market direction better than, or can we predict market direction better than a random guess? In other words, what do we want the prediction error to be better than? 50%. Does that make sense? We'll see what happens. Or the success rate. Okay, so I'm going to manually extract the test data and the training data just by using simple subsetting from our course. So notice that we just extracted 2005 as being our test data. I called that test. Does that make sense? And then train, it's everything except for 2005. Our data set only has those few years, okay? N.test is the number of rows in our test data. And notice, there's more elegant ways to approach this problem, but I'm just writing a loop just because it's kind of the first way to approach something like this. It doesn't take too long to run, obviously. But what we have to do here is I have to actually, to compute the test error, recall is this, right? That's what I was talking about earlier. This is the training error, but now we're doing it with the test. We have to actually predict every single case of our test data coming from our trained model, right? And that's why I'm looping from 1 to n test. Does that make sense to everybody? So there's a lot going on in this. So once we apply the loop, we run through the actual test data from 1 to the number of test values based on the trained lags. And then I'm storing all those into something called predictions. So somebody tell me, what is this vector predictions represent?
The results of the model.
On the what data set though? Test. On the test data set. Does that make sense? So let's say the test data set is 250 cases, right? Then you use the full 4 years of data to only predict 1 year of data. Does that make sense? And then we don't know how accurate our model is going to be. So this is a vector of whatever, 200, however many trading days are in a year, right? And then we just see how many were misclassified. So the sum, you could have done the mean without this. It would have worked as well. Okay? Because this is a vector of trues and falses saying when we misclassified, and then you could just sum and divide by n test, and this represents the test data. So what's our interpretation?
This is pretty bad, right?
It's pretty bad, right? It's like flipping a coin, basically. Right? Which it's not a big surprise. I'm trying to predict the stock market. So, of course, it's not flipping a coin. Does that make sense? Okay. It's very bad.
That's like worse than flipping.
Right. Well, this is the error. Yeah, it is. Yeah, on average. So it's very bad. Actually, that's not a surprise. That should be like, oh wow, I can't. We would have been. Everyone would have been rich.
Yeah.
So, does that make sense? Okay. So it's a nice example. Let's generalize this example a little bit. Let's see. Let's build our model using the same data. This time let's do k equals 7. So here is k equals 5. The only difference, I keep going back and forth. Notice I didn't enter the k equals 5 because I put that as a default value. Does that make sense in the function? So it looks like when you use a bigger window, we actually get a higher error. Okay, so very basic question. Would we choose k equals 5 or 7 if those are the only two values we could choose? K equals 5. Does that make sense? So the way you pick tuning parameters is you try to minimize test error. That's always the same technique. Technically, you would do it for multiple k values. We just did it for 2. Okay?
So I think test error is pretty much like the proportion of mispredicted observations.
That's exactly.
Since it is larger than 0.5, it's worse than coin.
Yes. It's worse than yes. So this is pretty interesting. And in fact, I'm a little skeptical on this. So I don't know. I didn't have time to run this code again. But based on this one data set, it appears that we can get the test error to be decent with pretty big values of k. But that seems a little suspicious. It's got to be careful. Like these models sometimes you'll choose. You're like, oh yeah, if I use 600, it's going to make me money. And then you end up getting a huge crash or something, right? I mean, it's just. Do you see what I mean? It's tempting to pick one of these higher values of k, but this might just be an artifact of something else, right? Anyway, just without the application, typically you look at multiple values of k and pick the one that has the lowest test error, okay? If you have ties, you pick it in the range of those values. All right. So, a little bit of reading. Introduction to Statistical Learning. We have classification and cross-validation. And then just remember the set of slides we went over for several days and discussed how to write a function R. And one thing I do want to mention before I move on, I posted another set of slides. I took them from the data mining course I taught last spring because we also taught K&N regression in that course, and we don't teach K&N regression in this course. But I want you to think very intuitively. This will only be like 5 minutes. Let's say your data set this time was not a classification problem, but was a regression problem. And your data set looked like this. Okay? So this is y now, this is x. So how does a K&N work in regression as opposed to classification? So this time, you only have one x. We don't have two. You could generalize this to as many x's as you want. But let's say our neighborhood is 2. So let's say k is 2. Then, and here's your test point. Then your radius is, or your neighborhood's around this test point, and you pick the 2 closest x values, right, to that test point. So how do you predict the y value? What are you going to do with these 2 values? What do you think? Super intuitive. Just average, thank you. So then the y value for this point is going to be here, right? So you can actually do a K&N, and if it was 3, right, these would be the 3 closest points, so the average would be maybe right here. So a K&N in a regression setting, it's exactly the same. You still can code it up using the order function, but you just average the y's instead, and you'll get something that looks like, let's say k is 3. I'm just going to eyeball this. You know, it's going to look kind of like a step function, right? That would be a K&N for regression. Does that make sense? But you should be able to convince yourself that it's exactly the same notion, but instead of looking at majority rules, you just take the average of the y's, and then that gives you predicted values. That's the training. So notice what would happen if you chose k equals 1. It would be forced to cross every point. Does that make sense? And if you pick k equals the whole data set, it would just be a horizontal line across the, right? That's overfitting method. What's that?
So that's taking intervals.
Say that one more time, I'm sorry.
It looks like taking intervals.
It kind of reminds you of that, but it's, yeah, it is actually, but you're not computing the area under the curve, you're just computing the height of the function. But yes, absolutely. Yeah. So, kind of looks like a Riemann something. Yeah. All right, so for the remainder of today's class, let's let's do this lab. And what we're going to do is do another financial data set coming from the Introduction to Statistical Learning. This one's not called SmartKit, it's called Weekly. And instead of daily returns, it's weekly returns. And what I want you guys to do is generalize the function to use all the lags, and then try to perform a cross-validation. So unfortunately, I'm not going to go over, you're going to have to learn cross-validation by reading the actual lab document. Does that make sense? And we'll spend probably another 30 minutes or so to finish this lab tomorrow, even though we're going to move on to different topics. Okay? But I'll let you guys work on that now. But you want to get some practice with this stuff. Okay, so we're back to classification. I also posted that set of regression slides. I'm not going to actually go over those slides, but if you wanted to read those as a reference, it also talks about supervised and unsupervised learning. And things like that.
So that is not a part of our, that is not in the scope of this class, right?
Well, it's definitely in the scope. It's easy enough. It's just just for time reasons, I'm going to skip it. But remember when I originally said models get split into regression and classification? You can do KNN regression or KNN classification. We spent the time on this, but what's on the board over there is this. Does that make sense? Point being, I'm hoping that that's very intuitive, despite, like, it shouldn't be hard to code that up hypothetically based on the information from the classification.
So I kind of missed what your expansion of that. Could you please just recap for a quick?
I just want you to know this exists. Because if you take a more advanced course where you focus purely on the actual models, this is going to be one model you see. And it's exactly the same as classification, except instead of majority wins, you're just taking the average of the responses. So it's just nice to, this shouldn't be hard after, it's the same idea, I guess you could
So that's
say.
why it's quantitative, so we can take that.
Yes, exactly. Yeah, this is just the quantitative KNN version as opposed to the categorical one. So. Okay. Let me unplug this for 1 second.